Our next topic of magnetic effect of electric current is the magnetic field induction at an axial point of a circular current carrying coil. Magnetic field induction at a point, at an axial point, magnetic field induction at an axial point due to a circular current carrying coil. So a diagram will be a little bit of tough diagram. It is because the situation is three-dimensional. So this is the circular coil. Okay, this is the circular coil through which the current flows. We have to find out magnetic field intensity or magnetic field induction at this point. And this is the axis of the circular coil. It passes through the center of the circle and perpendicular to the plane of the circle. So this is the circular coil. So this is the plane of the circle. So this axis, this is the axial line, or this is the axis of the circle. It passes to the center of the circle and also perpendicular to the plane of the circle. So we have to find out magnetic field induction at this point. This point is at a distance small r. Small r, what is small r in my expression? So small r is the distance. Small r is the distance of the point where we want to find out magnetic field induction from the center of the circle. So this is the center of the circle. So this is the experimental point. This distance is smaller. In your NCERT books, this distance, they are represented by small x. But here I have written this distance smaller. What is capital R? Capital R is the radius of the circle. Radius of the circular coil. So this is the radius of the circular coil. This is diameter. So half of this circle, half of the diameter is the radius of it is capital R. So this is the center of the circle. The circle is like this. So this is the circular coil and this is the axial point. Have you seen my thumb? So this is the axial point where we want to find out magnetic field induction. This point P is at a distance smaller from the center of the circular coil. So what is the procedure? Procedure is we have to apply the Biot-Savart law. What is Biot-Savart law? The Biot-Savart law gives us the value of magnetic field induction. The value of magnetic field induction at a point due to a current element. What is current element? It is a small section of current carrying conductor. What is current element? Small section of current carrying conductor. So in order to apply this, in order to apply the Biot-Savart law, I consider two current carrying elements. One is C and one is at D. I consider two current carrying elements. One is C and one is at D. This is ideal. This is ideal. At diagonally opposite ends. At diagonally opposite ends. Okay? That means this is the circular coil. I consider one current element here and one current element here. Okay? Now this is the position vector. This is the position vector. This dotted line represents the position vector. This dotted line represents the position vector of the point P with respect to the center of the current element. So if I consider this is the current element, then this is the position vector. This is the position vector. It is slightly inclined. Okay? So what is the value of what is the magnitude of the position vector? This is small r, this is capital R. So according to Pythagoras theorem, this length of this position vector is square root of capital R square plus small r square. So this is the diagonally opposite current element. This is also at a distance x is equal to square root of r square plus small r square. Okay? What is the Biot-Savart law? Mu 0 by 4 pi I dl sine of theta. I dl sine of theta divided by distance square. So distance square is this. I dl, what is theta? In this case, theta is 90 degree. You just see. So this is the current element. So this is the position vector. So what is this angle? This angle is 90 degree. This angle is 90 degree. Is it clear? Because this is the position vector. Yes or no? This is the position vector. So this angle is 90 degree. So in this diagram, it is very hard to visualize the value of theta is 90. But here I can show that this angle is the 90 degree. Okay? Again I repeat it. What is the procedure? Procedure is we have to consider two current element at two diagonally opposite ends. So this is one current element, this is one current element. Okay? So this distance is capital R, this distance is small r. So what is the length of the position vector? Length of the position vector is x is equal to square root of capital R square plus small r square. Capital R is the radius of the circular coil and small r is the distance of the axial point. So in order to apply the Biot-Savart law, what is Biot-Savart law? dB proportional to ideal sine of theta by distance square. So this is the position vector. In the law, this is the position vector. So in my case, so this is the position vector. The position vector join the center of the current element with the experimental point. So this is the current element, this is the experimental point. So therefore this line is the position vector. Okay? It is like this. Have you seen it? If this is the current element and this is the position vector, then this line represents the position vector. So what is the angle theta? What is the angle theta? Here theta is the angle made by position vector with direction of the current. So in my case, current flows like this. In my case, current flows like this. Yes or no? Current flows in this direction and this is the position vector. So therefore this angle is, can you see it? This angle is 90 degree. This angle is 90 degree. Okay. So therefore, for one current element, magnetic field induction is mu 0 by 4 pi ideal sine of 90 divided by distance square. Divided by distance square. So this is the distance. This is the distance. This distance is square root of capital R square plus small r square. Distance square. So square root will removed. So dB is mu 0 by 4 pi ideal divided by capital R square plus small r square because sine 90 is equal to 1. Now again one imagination is required here. So what is the direction of dB? Direction of dB is perpendicular to the plane containing the current element and the position vector. So this is the current element, yes or no? This is the current element, this is the position vector. So this is the current element and this is the position vector. So dB should be perpendicular to it. If dB is perpendicular to it, that means at this point, due to the current element at C, so this is the direction of dB1. And due to current element at D, this is the direction of dB2. Both dB1 and dB2 have equal magnitude. But their directions are different. Okay? So what is the magnitude of dB1 and dB2? dB is equal to mu 0 by 4 pi ideal divided by r square plus small r square. But what is the directions? Directions is in these directions. Their magnitudes are same. So I consider this angle phi and this angle phi. So if this is phi, this angle will be phi. How? Because this is the y-axis. This is the axis. I call this is x-axis and this is the y-axis. If this angle is phi, this is 90 minus phi. This is as a whole 90. Why? Because this line must be perpendicular to it. This angle is phi. So therefore this angle is 90 minus phi. This is again 90 degree. Therefore, this angle is 90 minus 90 minus phi is equal to phi. Due to the same logic, if this angle is phi, this angle is phi. So, you resolve dB into two components. This is dB cos phi and this is dB sin phi. Again, you resolve this dB into two components. This is dB cos of phi, this is dB sin phi. That means this dB cos of phi, this dB cos of phi get cancelled. Because we consider the current element at diagonally two opposite positions. These two current elements are diagonally at two opposite positions, therefore this dB cos of phi, dB cos of phi get cancelled. So it has one x component dB sin phi, dB sin phi. So what is the net magnetic field induction at P due to two diagonal opposite current elements? It is twice dB sin of phi. It is twice dB sin of phi. So it is twice dB sin of phi. It is twice dB sin of phi. Net magnetic field induction due to two current elements C and D at diagonally opposite ends. Twice dB sin of phi. So this is 2. What is dB? This is dB. Mu 0 by 4 pi ideal r square plus r square sin phi. But what is sin phi? What is sin phi? This angle is phi. This is small r. This is capital R. And this is x. Yes or no? So this is hypotenuse. This is base. And this is perpendicular. So what is sin phi? Sin phi is equal to perpendicular by hypotenuse. So perpendicular is capital R. So what is hypotenuse? Hypotenuse is square root of small r square plus capital R square. Therefore, sin of phi is equal to capital R divided by square root of r square plus small r square. You just see. So this is phi. You take this right angle triangle. You take this right angle triangle. This is perpendicular. This is base. This is hypotenuse. What is sin phi? It is perpendicular by hypotenuse. Therefore, value of sin phi is equal to capital R divided by capital R square plus small r square. Now, if I rewrite the equation mu 0 by 4 pi, this is proportionality constant, therefore written like this. This 2 is here. This ideal, this capital R is here. You just see. What is the power of capital R square plus small r square? It is 1. But what is the power of capital R square plus small r square here? It is half. So 1 plus half is equal to 3 by 2. You just see. Power of capital R square plus small r square is 1 here. And this is power of capital R square plus small r square is half. So 1 plus half is 3 by 2. So it is mu 0 by 4 pi. Twice ideal capital R divided by r square plus small r square whole to the power 3 by 2. Is it clear? So this is the net magnetic field induction at P due to two diagonal opposite current elements. Now, what is the net magnetic field induction? What is the net magnetic field induction due to whole circular coil? So I have to integrate. Other terms are constant. Only variable term is the length of the current element. Only variable term is the length of the current element. So I have to integrate. So it is integration of dl. What is integration of dl? Because when I consider one current element here, next current element here. So if I consider one current element here, next current element will be here. If I consider one current element here, next current element will be here. If I consider one current element here, next current element here. That means when I integrate half of the circle, the other is already included. Because at every position, I have to consider two current elements at two diagonal opposite ends. Therefore, if I consider one current element here, so in this position, the other current element automatically comes here. So therefore, what is integration of dl? Integration of dl is pi r, half of the circumference of the circular coil. Half of the circumference of the circular coil. So therefore, B is mu 0 by 4 pi twice IR divided by r square plus r square whole to the power 3 by 2 pi r. So 1 pi get cancelled here, 1 2 get cancelled here. So it is 2. Pi get cancelled, 2 get cancelled 2. R square plus r square whole to the power 3 by 2. This mu 0 is here. These are and these are r square. So what is the total magnetic field induction? What is the total magnetic field induction due to this circular coil at the point P? It is B is equal to mu 0 I r square divided by twice r square plus r square whole to the power 3 by 2. And direction is along the axis of the circular coil. along the axis of the circular coil. Okay? Now, if the circular coil has n number of turns, if the coil has n number of turns means if the coil has n number of turns, that means like this. If it is like this, if the coil has n number of turns, the B is equal to mu 0 n I r square by twice capital R square plus small r square whole to the power 3 by 2. Whenever I write capital N, it always represents total number of turns in the coil. Okay? One special consideration is required. If magnetic field is required at the center of the circular coil, if magnetic field is required at the center of the circular coil, that means point P will come at the point O. If the point P comes at the point O, what is the value of small r? Value of small r is 0. I mean, if in the exam they ask to find out magnetic field induction at the center of the circular coil, we have to put small r is equal to 0 in this equation. Then it becomes capital R square whole to the power 3 by 2. So these two and these two get cancelled. So it is twice r cube. This is r square is here. So 1 r will get cancelled. So B is equal to mu 0 Ni by twice r. So this is the value of magnetic field induction. This is the value of magnetic field induction at the center of the circular coil. The question will come like this. Using the Biot-Savart law, find the value of magnetic field induction. Find the value of magnetic field induction at an axial point of a circular current carrying coil, and hence also find the value of magnetic field induction at the center of the circular coil. Find the value of magnetic field induction at an axial point due to a current carrying circular coil, and hence find the value of magnetic field induction at the center of the coil. If the question comes like this, you have to do like this. But sometimes the same question may come in this way also. So instead of find out the magnetic field at axial point, they may ask to find out magnetic field induction at the center of the circular coil. If it comes only at the center of the circular coil, our calculation becomes very easy. So this is the circular coil of radius r. I consider a current element here. This is the current element. So this is the position vector. So what is the angle theta? Here what is this angle? This theta is equal to 90 degree. Therefore magnetic field induction at center due to current element Hc is dB is mu 0 by 4 pi ideal sine of 90 divided by r square, because this angle is 90 degree, theta is 90 degree here. That means whatever be the case, theta is always 90 for the circular coil, whether it is axial point or at the center of the coil. So sine 90 is 1, so mu 0 I dl by 4 pi r square. Therefore magnetic field induction at O due to whole circular coil, I have to integrate it. But this time the integration is whole integration, because we consider only one current element. But in the previous case, when we find out the magnetic field induction at axial point, we consider two current elements at two diagonal opposite ends. Therefore our integration becomes only half of the circle. But here we consider only one current element, so therefore we have to integrate in the whole circle. Therefore this circle is given here. So what is integration of dl around the whole circle? It is twice pi r, circumference of the circular part. We know that integration is nothing but addition. So if I add all the current element in the whole circular coil, what we get? I will get the circumference of the circle. This is twice pi r. These 2 pi and this pi get cancelled. These 2 and 1 4, 1 2 get cancelled. So this is mu 0 I by twice r. So this is the magnetic field induction at the center of the circular coil. This is the magnetic field induction at the center of the circular coil, and this is the magnetic field induction at an axial point due to a current carrying circular coil. But if they ask to find out magnetic field induction as a tail question at the center of the coil, you just put small r is 0 here. But sometimes in the examination, they ask to calculate the value of magnetic field induction at the center of the circular coil instead of asking the value at axial point. So if they directly ask to find out the value of magnetic field induction at the center of the circular coil, we should follow this method. In this method, only 2 marks is given, but if they ask to find out magnetic field induction at an axial point, 4 marks will be given to you. The question will be like this: state the Biot-Savart law and hence find the value of magnetic field induction at an axial point due to a current carrying circular coil. And they may give a tail question. What is the tail question? Also find the value of magnetic field induction at the center of the circular coil. Okay, I stop today here.